Hi there, welcome back to the stream. I'm Jun Chan, and today we're back at looking at the Chronofold data structure, which is to have a real-time syncable and efficient text data structure, and trying to make way towards first understanding it and then implementing it in Purescript. So just start with my standard disclaimer that I like to follow tangents, and that I do this to try and learn how it is to work even more in the open, and then also learn in the open. So this might be a little bit disorganized, and it might not advance towards the solution in the most straightforward way, but hopefully you can still get something out of it. Yeah, and let's see. Last time we were looking at the original paper, including some of sort of the attached documentation. Sorry about that. The attached documentation, in particular the YouTube video that the author of the paper released, and which has this really useful diagram. And I've collected a number of a number of links that I talked about last time, and I posted that together with the YouTube video that that got exported from Twitch yesterday, with the problem that I started it without sound, and so I think sounds only starts like way into the video. I actually didn't even check, so sorry about that, and hopefully today we don't have this problem. And yes, the show notes are and then the relevant links have been posted there, and I'll do the same today if we have new links. So let's see, maybe I can make this actually fairly self-contained, so that the links we have today are the links we pay attention right now. And so this would definitely be one of them here. Okay, so I was, before we were getting back on stream, I was reading again, maybe a bit too fast again, the paper, and realized a few things. First of all, I think I was confused with the notion of an op and the notion of what we store in the struct, and it's very well said here, which is that actually a Chronofold entry, which is this guy, takes less space than an op due to its absence of timestamp. So yeah, so it means that an op is not a Chronofold entry. And what we're really storing on disk or in memory in the Chronofold is this struct. And then it just occurs that to rebuild ops as needed, then we have this adjunct data structure, in particular ref and dx alpha and this alpha -1. So that's one thing. Then the other thing I realized is that the section 2 is really about explaining in detail what an RCT replicated causal tree is like. And it could be that, and it also references a bit earlier on, some specific aspects of previous implementation of CT, specifically I think Swarm in 2012, and then RON, the 2017 version, with slightly different way to deal with a CT. So, and this is an evolution of this and the Chronofold specifically. So it might be that actually going and referring back to some of these implementations will be useful if, in case I actually, I can't make the jump directly to the Chronofold because I never implemented a CT before, and that actually implementing a CT will be useful. So especially because there's already code written by the author that does this. But for now, let's try and be brave or foolish and try and directly go to the Chronofold, even though this means that there's a little bit more things that I might be missing and not familiar with and struggling with. Okay, so last time we were also playing with a representation of what is in this slide here. Let me see, can I make it higher resolution? Yeah, there you go. And I was interrogating myself with regards to the things that are actually also described in the paper, namely, what is it exactly that we send over the wire, given that the indexing is that there's a local indexing, but that there's a way to retrieve to link a remote op with a local index, and that's, I think, part of the whole subtleties, at least of what I was about to try and understand last time. And that's something that's also probably well explained in the section before the one that I was focusing on, which is the difference between a log of timestamps and a log of indices, or a log timestamps and a log indices. And so I believe that in this terminology, a timestamp is and I think this has a definition, so let's make sure we don't make a mistake here. A timestamp is an ordered pair T and alpha, where alpha is the author and n is the author's index. So in here, it's and then it's author index, yes. So this number underneath is the log timestamp, and then the number at the top is the log index. And so what I was intuitively trying to differentiate at the top and at the bottom there were these exact two things. So, and yeah, let's see with just to explain what this thing is. This is an attempt to reproduce the example that's mentioned in this article. Which is another article about causal trees, not Chronofold specifically, but just to have another example to look at and think through how the data structure work. And then here below, right here, I have the attempt to reproduce this example, which is the same example that's in the paper, but with a little bit more detail than this representation here. And so at the top, indeed, we have the log index, which is subjective. So each replica has a log index that's going to contain something different from the other replicas, and that's part of the magic here. And then the interesting thing is that this is actually not a representation of the Chronofold data structure. It's more of a logical representation because a Chronofold entry takes less space than an op, and this really are ops here with all of their detail. But in fact, a Chronofold entry is not an op, and as mentioned here, so there's two ways that it's mentioned, that the Chronofold entry takes less space than an op, but also that to build the Chronofold building algorithm uses information that is not included in the Chronofold itself, and those are exactly the ref and the NDX alpha, NDX minus alpha. So let's make sure we understand this again properly. As I understand it, the entry in the Chronofold is actually more of the weave data structure, meaning it's meant to help reference where the splicing occurs without having to actually splice an array in memory, which would be expensive. So that's it basically. It is kind of a linked list, and that's pretty much it. And the way that it becomes a CRDT or an op is through the existence of these separate data structures, which actually help form the actual CT. So last time, what did I write? I wrote something that was kind of my current summarization of what I understood, or something I was trying to understand. So let's see whether that's at all correct or not. And let me also double check that I have the chat on screen and so on. Yes, I do. Okay. The next NDX value in the Chronofold struct points to the next entry to maintain an append-only representation. Yes, and so I would say that that's the more important part. The next entry to maintain an append-only representation of the linked as of the weave as a linked list. I think that would be a bit more correct. And then we derive the parent, the CT parent from, and that's where I was wrong, because I was, I think, trying to derive the CT parent just from the weave. But no, we have a ref data structure that will help us do that. So so that's wrong. So let's it's not. I mean, we derive it. We obtain the CT parent from the ref data structure. So that would be more correct. And then there's something quite interesting, which I was also having an intuition about. Basically, the conversion between log indices and log timestamps, which is a bit of a conversion between sort of the local coordinate system to, well, actually, I think accurately, it's the conversion from something received from a remote system coordinate to the local coordinate system, but which implies also that when it was sent as a converted op, as an op that's in a more global coordinate system, if that makes sense. Let's see. So that intuition is explained here. Given that a process may convert logical timestamps to its log indices once it receives an operation from another process, then it proceeds with the indices. And then when sending operations out, it performs the reverse conversion. This way we insulate data structure from the complexity of a distributed environment, which is basically another way is something to say, I mean, it is data hiding in some sense. It's a kind of an invariant, but it's a way to say that local data structure know about their local indices, but when they send them out, they send them out in a way that can be then interpreted properly to local indices on other replicas. I think that that's really the crux of it. So, so how does it work is the question. And then which order exactly is it in? So a process may convert logical timestamp to its log indices once it receives an operation. Right, so if we receive, let's say, a beta 7 at this step, well, actually, yes, no, we don't receive beta 7 at this point. We're locally appending beta 7 on replica beta. So that might not be the case we're exploring. It might be more the case where, let's say, here we're on gamma and we receive the beta 8. So the question is, what does beta 8 comes with? And I think from here it comes with a logical timestamp, right? And that's exactly what beta 8 sorry, not beta 8, beta 7 here. What beta 7 here, here is a local timestamp. So we can convert it to a log index, but is it to its log index or to our log index, right? I mean, we don't convert anything when we receive beta 7 and then we append it locally as f gamma. So that's not it. The thing we need to convert is we need to know in beta 7, and the whole key is to do the conversion also for the ref. But but we also need to do the conversion for the linked list. So the question is, what is sent over? And that I'm still not sure. So let's see. I think maybe rereading what goes on after this might be the key. So let's see. So yeah, right. If we index it, if we edit the text locally, then a Chronofold itself suffices. So we don't need these, which is the part of the beauty of all this. We can just append, and we don't need to. And we just we need to only to maintain the weave linked list. Okay. Namely, as per Remark 2.3, the timestamp of a new locally authored op is greater than other timestamps in the log. So, so I think this refers to, let's say, beta starting to add beta 7 after receiving Pinsk. So would be somewhere here, and then beta edit its own data structure locally, or even better, maybe we have alpha starting with, let's say, 0, the root. Oh, that's what the root is. Yeah. So roots that I was wondering whether that's what it was while reading the Rust source code, and now I see that indeed that's what it was. So 0 is the root, and then when we are alpha and that we're appending alpha 2 after this, then the timestamp, we can say the timestamp of the new locally authored op is greater than other timestamp. So alpha 1 to alpha 2. And it excludes the case of the primitive sibling because we don't have replicas, and so we don't need to maintain ndx -1. Okay, so I think maybe let's reread then the section before. Note that the Chronofold building algorithm, right, uses information that is not included in the Chronofold itself, namely that it's a tree-forming ref relation, and so that's, so really maybe I should summarize this actually a little bit more clearly also here, because we have replica, we have what a timestamp would be, we have what an op would be, and then we have what a log of that would be a log timestamp, but that's a log of ops, is it? And then the Chronofold would be a different thing, right? So okay, let's write that Chronofold for now would be a, well, it would be, let's say, an array of good points, so a value well, we could call it value, type value, and a next. Which points to, well, really a natural, because an index of an index in the array. And I don't know if we want to be fancy about, I mean, right now we're not going to be fancy. We're going to say it's an int. And then maybe we want an array parameterized by its index type. Well, maybe we want a natural index or an array parameterized by its index type, but right now we can do this. And maybe this should be just a type synonym. It probably should be a type synonym, so let's just say type and call it array. Okay. And what am I doing here? I'm saying that it's a type. So Chronofold, and then so that means that we also have a ref, and so a ref. A ref is the CT data structure, and well, right now we don't know what it is. There's more detail right here about the timestamp to index mapping, which is such that at alpha, right, actually this is taking the result of the ref. So I think a ref is something that takes I beta and the coordinates of the remote structure in I beta. So okay, so let's try this. Maybe we can make ref a function type for now. Let's say something like it receives an op. Does it matter that it's an op at replica beta? It probably does. But let's say now op is somewhat opaque and contains that. Is that the case? Yeah, because the timestamp contain the timestamp contains the replica, but that's yeah, I think. Oh, okay. No, of course. So the question is, when is the log of operations? Is there such a thing as a log of operations? Or is it just an array of operation and that's logically a log? Because then we have a ref in that case. But I think we're trying to rebuild this from parts. So even if we logically have this, somehow, and maybe sometimes we need to think about something as an op, we're actually reconstructing these ops from these simpler composite data structures. So in any case, the ref here will need to store so that we can reconstruct a log. And so when we receive or an op, so when we receive an I beta, which really I think is a timestamp and a value. And that's really what it is, isn't it? Let's make sure we have the notation correctly. The I, I'm not sure whether that's the same I, but this tuple notation is this, no? Yeah, alpha I equal n beta. I think this is what we're talking about, and so this is a timestamp. We receive a timestamp. No, we receive an op indexed by its timestamp. And an op, that's a timestamp, and the op would probably be something like this. Up. I think there was a description of a log of ops. An op is a tuple t, where t is its ID, and t is a timestamp. Yeah. So we receive the ref, and so it's implied that we receive the ref and the val. And so I just need to understand also in which coordinate system we receive the ref. And I actually want the ref to be first here, I think, for sanity. Okay, so in fact, when it says we receive an op I beta, we receive an op with timestamp t, but it carries with it its ref and its val. So really, op is what's transmitted to across the network, and it has it can be uniquely identified by its timestamp. Okay, maybe I should write that down, huh? An op is what is transmitted across replicas and is uniquely identified by its timestamp. Timestamp t. Timestamp t equals, and then we can even say I beta if we want. And in this case, we can mean that we're receiving this. Okay. So I'll want to add to these diagrams. This is not the Chronofold. This is more like the RCT maybe. In any case, it's more like an array of log, an array of ops, or a log of ops maybe. Is that the correct term? Maybe. So let's index this somehow, because that's not the Chronofold, and that's something I didn't understand yet. Okay. Let's make it so that I can understand where this thing breaks. And so this is, let's call it a log of ops. I'm not sure that that's proper, but maybe it's more a RCT, which is the T, a set of timestamps, val, a function with domain T, and so a function with domain T and codomain cut point. So we have that, and then ref. Oh, so no, ref is I've started putting ref here, and log, a function from the set. Right, this I didn't quite understand. A function from the set proc r authors to the set of injective sequences in T. It's associatively process alpha belonging to proc r to the sequence log alpha blah of timestamps in T with alpha I different from alpha j. There's some invariant and such that alpha beta proc r and I lower than the value, the length of an alpha, then we maintain some ordering invariant. So I think that that's a way to talk about the fact that this structure can have subjective ordering, but that they maintain this ATO. This ATO, which means arbitrary total order, which is just a way to recreate a total order from this sort of partial order of replica relative timestamps. Then the causal tree that RCT produces directed graph, and so with the ref we can retrieve the causal tree, so that's fine. And so that doesn't necessarily answer my question about whether that means that the log, I mean the log is treated here as a data structure. So maybe we say that this data structure with this invariant of subjective ordering and the annotation from the timestamp of the replica, that's a log. And so indeed, then in that case, this guy is a log, and it's just a log. It's not even a log of ops. It's just a log, I think. And then we can rebuild an RCT from that. If we have ref and val. So maybe log is actually, maybe log is actually this conceptually. And this is val. And then this is it annotated like that? There's no such thing as a log in this diagram, but I mean, it might be a stretch, but... And then this would be timestamps, right? No, this is timestamps, right? So, yeah. And these are indices. So really, yeah, maybe it's timestamp. And indices. Maybe I should pollute with annotation this this guy here. Well, end will do. Val is fine, and well, timestamp like that. And I think that, let's say that that's a log, and then we have a log of indices and we have a log of timestamp, and then, well, we have a way to do values if we want. And yeah, this is not very easy to read, but I'll clean it up afterwards. And a knob. Its ID is a timestamp, so alpha, let's say 2. Ref. Causal parent. And val. 0. And so, right, the ref that's the key, is that ref is in the coordinate domain of timestamps. Okay, yeah. Log of indices is the local coordinate system. Log of timestamp is the shared coordinate system. And so that whole conversion thing is that, and the real key here is that when an op is sent within the shared coordinate system. Yeah, of course, that's the whole point. Okay, so how do I write this? Well, for now, let's just write it here. When an op is shared, it's shared with values in the shared coordinate system, also in timestamps, let's say, and which is the shared coordinate system. And so if we're back to, let's say, we're gamma, and we receive beta 7 as the ID, and then we receive a ref, which would be alpha 6. No, hold on. That I think maybe I misunderstood this thing, because I was thinking that we could rebuild the ref from the previous next, but obviously we can't. So let's look again. And then, so when we receive beta 7 includes its CT parent, which is alpha 6. No, so that I think is correct. And then when we get, okay, no, so ref at time 7 really is, for beta 7, we receive alpha 6 as the ref. That sounds correct. And then M actually has, well, let's say of relevance, if we're kind of even using a more of a sparse array style notation here, then we can say, well, it doesn't matter. Then we don't write it because it just follows naturally, aka it follows beta 7. So therefore we don't need to write it. And then we just ship over the wire alpha 6. So I kind of want to try and say, well, what really is the Chronofold, and that's the ref data structure, right? So that's the ref. That's simple, and that's not in the Chronofold. But in the Chronofold, we are indexed by the local index, which is in fact called NDX in the paper. So maybe I should call NDX over there rather than IND. Makes more sense. And I think I had, did I call it ID here? I did. But in this case, that is actually not the ID. In this case, this is that's the ANDX, isn't it? Well, it's the timestamp, which is the ANDX together with the author. Yeah, it is. And so it's the timestamp. Now let's call it timestamp. It's ugly, but so maybe ID was better. Uniquely identified by its timestamp T. Or maybe we call it T. Yeah, T is good. Like that. Naming is hard. T. Yeah. Okay. Maybe we know. We put annotations here. Uniquely identified by its timestamp. We'll copy that. Okay. Well, in alpha 2, actually, that's P. That's not 0, right? No. And so, back here. Here we have T again. No, that's not a timestamp. That's an index. So we have an NDX. That's a val, and that's a T. But we don't really care Okay, something I'm missing is what is the in the Chronofold. Yeah, no, that is, so it is in the Chronofold is indexed by its NDX, and it's just that we don't have. So I think I don't want to be first explaining what's in the log. I want to first explain what's in the Chronofold, and that has its index, its value, and its next. And we can elide the next. But then we have ref. So let's call it co-structures. So ref, well, right, NDX takes a timestamp. So NDX is the thing that takes a timestamp to a J, which would be an NDX, I believe, right? So let's start with this guy. NDX. Takes a T to its NDX. Which usually is trivial. And just copy this. And then NDX minus 1 just does the reverse. So that's not super interesting, but that's where it is. And then ref and let's write it explicitly here. And maybe we should write next explicitly at the beginning, in fact. Maybe that makes sense, huh? Next here is actually 2 alpha, and it's in the local coordinate system, so that's correct. Okay, and then we need to introduce this bottom or terminator, or I don't know. Yeah, I think that's tombstone, but I'm not even sure. X. Let's make it bottom. And that's the next. And then the ref. The ref would take. Does the ref take timestamp to its next? So then it would be in the shared coordinate system. And I think it does. Yes. Indeed. Ref takes a timestamp to a timestamp. I guess conceptually this, right? Let's make it haskell-y. Let's not make it haskell-y because we aren't using cap upper cap. Let's just make it terse. Okay. And hey, one hack, what's up? You're missing the party in the chat. Yay. Thanks, Hyperfocus Machine. So I was. Yeah, it took me a while. It seems like since I fixed some of my audio things, I broke some other audio things. Oh, it could just be that I didn't start Chatty. I think that's what it is. So therefore, I don't get dinged. So let me launch that. And connect. And it works. Okay. So how are you doing today? I reread some of the paper and I realized that I was mistaken, but now it feels like I have more clarity. Yeah, I'm good. So definitely moving forward in my understanding of the paper, even though I'm still writing pseudocode. At least I'm writing function signatures, so that sounds like progress. And so what I found out is that this guy, the Chronofold, really is only a kind of an array of val and next. And then the key is that there are, in fact, 3 other data structures that all do some smart stuff, and some of it can be understood as converting from the local coordinate system to a global or a shared coordinate system between replicas. And I think that's a big aha moment for me after rereading that sentence, which I kind of missed in my first read of the paper. A process may convert logical timestamps, which are the things that we call T here, alpha 1, into log indices, which are the thing that we prefix with the number, which is 1 alpha. And so this will make more sense as I expand on the examples, but it's been good. Okay, yeah, I could do that. It's true that I have it pretty. You're talking about the sound, right? I'll make a note of it and stream things. Less haze and volume, right? Okay. So let me know if it's really too hard to test 1, 2. Are you talking about the tone of the bell, or are you talking about my voice? Right. Yes, you're talking about the bell. Yes, the bell. Okay. Yes. Well, how can I diminish the volume of it? By going to Chatty here, and yeah, I went a bit overboard. I actually chose that bell sound, and I guess it's long because because I don't get viewers that are regularly coming in yet, right? So I think it will progressively get shorter as maybe people start tuning in. But let's see. I'll at least diminish the volume to 4 times less, and I'll test it. Yeah. You know, I can't really, I mean, I guess that's not exactly true. I can do this. Yeah, I can make the sound this, and then that's better. Yes, face cam. Yeah, and I don't have that ready, but it will happen. Definitely will happen. And I can see that actually my changes didn't work because I probably didn't do this in the right. Always enable ding save sound ding blah test sound, chat message, save. Yes, thank you for the test. It does work. That's better, right? It's on. Excellent. So fix bell, and you know, there's no task too small to not congratulate ourselves for having checked one. So let's do that. All right. Okay, so ref, right? And so the key here is that ref is in fact a, and we can see this from its example use here, which is that this tuple I beta, that's in fact exactly a timestamp. It's basically yeah, it's a number, it's a replica number, and it's a replica name or a process name, and it's attached index, and it's and so ref is a function from a timestamp to a timestamp. So yeah, so ref, if we take it as an example here, we'll take we'll take our timestamps to our, let's say, well, it's really ref of t, right? So and that's 0 here, or is that right? No, it's not right. Yeah, no, it is. So 0 is a special case. So in our case, it's if 0 has value 0. So yeah, 0 is only used. Oh, that's an interesting thing for the data structure. 0 is not a val. I think 0 is a... It seems like 0 is a timestamp. Then it would mean that, let's see how it, I mean, here it's noted as 0 is a val, or, you know, empty set is a val, or root is a val. So, well, if that's the case, then in any case, false. So bottom, I guess, huh? Again. Yeah, maybe that's fine. It's not really that. Well, let's call it 0. There's overloading here. I'm not so happy about it, but and then here would be alpha 1, because that's all. That's the causal parents. And so in the sparse representation, we wouldn't even need to write any of that stuff. Yes, 0. Indeed. Well, yeah, you know, there's, and I haven't started programming in Purescript yet, right? But if you haven't seen that before, it might be a little bit confusing. And this style of programming languages like Purescript and Haskell, like people usually that do that, they're interested in math. I mean, not all of them, of course, but I myself, when I got into these languages, I also got into the math that's behind it. And then when you get into the math that's behind it, then there's some really interesting stuff that goes on in terms of defining, yes, what 0 is, and then what 1 is. And 0 is a usually, well, it's the empty set is one way to see it. And it's the initial object in the category of natural numbers. Yeah, 0 and 1 are like on and off. That's or off and on. In fact, right? Is yeah, is a good approximation. That's like a truthiness. It's truthy. It's I was actually reading an article about this today. It came from the Haskell Reddit, which was about lowercase Haskell. It was pretty cool. It might be a not too scary introduction to this style. And look, there's a section called 0 and 1. But look, this is confusing, no? But yeah, 0 and 1. And here, bool 0, 1, that's exactly what you're saying. That's the truthiness of 1 and the falsiness of 0. If you use this function bool over a number 0 or 1, then you'll get a false or true value. But in things like dynamic languages like JavaScript, then you can put 0 instead of false and 1 instead of true, and it just works until you crush yourself on the nose because of some weird stuff that happens. Do you know, have you seen the JavaScript what lightning talk? That stuff is pretty golden.
Go. All right. Means what?
Right.
Exactly. Let's talk about Ruby. In Ruby, if you reference an undefined variable, of course it name errors, as you would expect. And if you try to assign B to A with them undefined, of course it name errors, as you would expect. And what happens if you try to assign A to A with A undefined? Correct. Nil. What?
Yeah, I highly recommend it. Okay. What am I doing here now? Yeah, I'm talking about ref and the fact that it's, yeah, that's the epiphany from between yesterday and today, is that I think this kind of captures like the 4 data structure that kind of we need to get started to get things working. And then we do need the up data structure, which is so let's try to think of this. So when I'm at this point, like let's say 2 alpha, and I want to ship something over the network, then I think I ship right, I ship not my ID, but my timestamp, a ref, and a value. And I think that's supposed to be it. That's supposed to be sufficient to then receive it and do the things, do the merging and all that, I think. So we need to go through that, but yeah, intuitively, so if we ship the ref, then we use the ndx -1, the ndx first to get the index of the thing locally, and then we're good to go. That's basically what the trick is here, I think. So can I clean up my whole mess below with this new approach, and can I write this in a slightly more terse manner? And let's try all this. So, oh, right. So I don't need to store next and previous, although what am I doing here? ndx. Wow, I've confused myself pretty hard there with my annotation. I think that's because I haven't started to finish. I haven't finished indexing my beta stuff. But this is from alpha, and this logically goes in around here. Oh right, I called it 1. No, that's not a good name. But here, that would be an example that at time 6, the next of 6 alpha is bottom of 1. So say bottom. Calling it top is actually makes more sense, doesn't it? If we are secretly categorical. Top. Kind of looks like T, but blah, blah, blah. Yeah, no, previous 6, that doesn't make any sense. Next is T, fine. I think I shouldn't mix up my clean, simple understanding of the data structures with the follow-up, more example-like things that I'm going to do now. So let's pick back this guy. And say happy with next. Then it means that previous is 5 alpha, isn't it? And do we need previous? Maybe we do. But it's not ndx minus 1, right? That's something else. Maybe we don't even need previous. So I think maybe I'm confusing myself by having a previous. And however, when we start adding moving into the alpha 6 beta 8 case, then we have 7 alpha, which is backspace, and it's called okay, I shouldn't actually write it like this, should I? Because really what we're receiving is an op. And we're receiving it around this time. And it's at, so for us, its timestamp is beta 7. That's what we receive at this moment. And an op also sends us its ref, and so its ref is actually alpha 6. And its val, which is Yeah, you know, if I did that, then it would take even more time than it's taking already now. It's pretty involved, right? Yeah, no, I understand what you're saying, but you know, at some point, all of this is going to be, in some sense, buried inside the code, right? And people are just going to use it, and so hopefully that will be fine. So the val is the backspace, and then so we receive that, and then next we actually receive beta 8, and the ref for beta 8 is actually beta 7, and the value is m. Yeah, you know, right now I think I'm being just a tiny bit selfish so that I understand what I'm writing first, and then I think I'll work on. I think it's already pretty cool if I can, you know, the way that I'm writing this, it's actually going to be pretty much what my tests are going to look like. Or I'm going to at least annotate my tests with these examples. And so the fact that they refer to the nomenclature, to the terminology that's used in the paper and in the video, I think that will be useful for people who are trying to re-implement it. So I am thinking a little bit about it, and tell me. I'm going to put on music and tell me if it's too distracting. Okay, where is this playing? Oh, it's playing on my actual sound system. So I'll turn that off. And I will select the proper audio output for it. Right. Am I going to be copyrighted, copy striked if I give that guy a listen? I found out about this, you know, stream-friendly music service called Pretzel, and that's what's playing now. Ah, yes. Thanks. I will take a look at it. Thank you. Okay. Where was I? Okay, I'll put it a little bit up. And yeah, tell me how it is for you. Right, so I was saying that I will write tests that use this this approach here. Okay, cool. Yes, absolutely. I'll put an oh yeah in there as well. Okay. Okay, so I'm saying this will be in as tests, but also to try and unroll manually the algorithm, which is really also what I'm going towards here. Until now, I had so many missing pieces to be able to unroll the algorithm even manually. So and so that's the Chronofold, and then we do have this index structure available to us. So maybe I should, yeah, I was saying that I want a quick, so I mean, index is actually trivial, it's included in that. Index -1 is also somewhat in here. So it's just that, it's just a ref. is that alpha needs to store its refs as well. And so, right, so this is the empty ref, which really is bottom, let's say. What? Yeah, but bottom, and then this is alpha. Oh, hold on, I don't even have the timestamp here. T. Right. So T is basically the representant of NDX and NDX minus 1. Yes. So I'm going to write that here. Morally NDX plus NDX minus 1 and ref. And then we should be set. Chronofold, our index, our ref, like in a shorthand notation, and then we receive external ops. Okay. Now let's try again with reading this whole thing. The algorithm for measuring new ops in a chronofold resembles well-known CTRD algorithm. Once a process alpha, which is us, receives an op I beta, so I is 7 and beta is beta. It appends an entry to its chronofold. So it means that immediately after that, our chronofold looks like 7 alpha one equals 1. I hope it does. Usually it does. Value is backspace. How do we calculate the next? Do we need to send this over? We do need to send this over, don't we? The op needs to have its next. Appends next, it has to find the op position in the weave, so that's the thing, and relink the linked list to include the new op at that position. That's what I'm trying to think of now. But if the op that we received didn't include well, yeah, it needs to include the next. I don't see how that wouldn't be the case. But in the definition of op, but arguably not the definition of op in the Chronofold chapter, but still, the definition of op is T, ref, and val. So only ID, ref, the only ID, CT parent, no, timestamp, CT parent, and value, the character. You know, I need to raise the volume of the bell again now, because I didn't hear it when you wrote something with the music. Okay, I think that works now. Oh yes, excellent idea. I'm gonna get myself some water. Thanks. Yeah, you're absolutely right. You know, okay, I'm going to write this in a log because that's something that I've been thinking about, which is yeah, either to actually adopt, like, you know, have you heard of the Pomodoro technique? Which is 25 minutes work and like 5-minute break. And, you know, have a little timer for that. Yeah, it's meant to for hyper-focused humans, I guess you could say, and make sure that yeah, there's a little bit of time off to let the brain breathe. Yeah, I think this all varies depending on folks, and I'm bad at following this. I think, you know, maybe because I'm more reluctant to take advice from a timer than a human. But yeah, taking breaks and drinking definitely important. All right. Let's see. Where was I? Yeah, I was pondering whether the next index is transmitted over the wire or not, and I don't see how it could not be. True. Yeah, you think? Yeah, most probable. Yes. Yeah, a colleague of mine talked about reaching the point of diminishing returns, which is a kind of a economics or game theoretic, maybe even way to think about it. The moment where you're not being productive anymore, so it doesn't make sense to add more time. It makes sense to just take a break. So let's see. Next. Yeah, this is the key here. It has to find the ops position in the weave. Okay, I'm going to explain this, and you tell me if you understand. Okay. We have this data. We are alpha, and we have this data. All of this thing, you know, neatly in a little array, and then we receive. We want to receive the backspace thing from beta. We want to receive the backspace character from beta. And so together with it, we receive this reference, which let's ignore it for now, and a timestamp, meaning we know that it's called beta 7. Fantastic. And then the backspace character. But the thing is, if we don't know where this backspace is typed, then, you know, we might as well be deleting K, right? But the backspace actually is supposed to be applied on P, because we don't want PISM, we want Minsk. And so, so basically, so let's look back at the ref. The ref, as I understand it, really only tells you, oh, hold on, maybe that's where I'm wrong. Because here, causal tree shows this attached to M. Huh. I see. I think that's the whole. I think I'm starting to understand. Ref is the causal parent is not the thing that came just before. It's the thing that you act on, and then somehow it still works. So in this example, alpha has already typed. Yeah, alpha has already typed that whole thing, and then beta types its own thing. But then when you receive the info from beta, you need to know where beta was, kind of, right? Yeah, and I think, yes, I think basically the thing that my aha moment right now is that I just was misunderstanding ref. Because in fact, ref doesn't point to, I thought ref pointed to the thing that came just right before. But actually ref, as can be seen, I think in this diagram, actually points to M, which then makes it so that it's solved. We know how to, if we know where that backspace is linked to M, then we know that we need to delete M. Okay, so that's good. That's excellent even. It's just that I completely misunderstood. Well, actually, that's correct here for alpha, but for beta, we send not alpha 6, but alpha 3 alpha, or no, alpha 2, yes. And then we fixed it by magic. If we only receive this, then we're good. Yes, yes. So ref, so let me try to write ref alpha 2, alpha 1, alpha 2, blah, blah, blah. And then adding beta 7. What am I doing here? Right, like this. Oh, this is meant to be in 7 alpha. So at position, at local index 7 alpha, we receive an operation with timestamp beta 7 with the causal parent alpha 2 and the payload backspace. And so it says next it has to find the ops position in the weave and relink the linked list to include the new op at that position. And so to do that, it locates the new ops CT parent. So we receive I beta, which is beta 7. And then ref of beta 7 is K gamma. Aha. So this is K gamma. And I think that's where things make sense in relation to the paper. This is I beta, and this is ref of I beta, which is K gamma. And K gamma, in order to know what is its index, we need to use the T index to say, well, alpha 2 is at 2 alpha, and so we know it's P. That's it. A small sidebar on the top right, just for music, while keeping the chart in the same place. Oh yeah? I was thinking that if I have everything at the bottom, then I can remember that it could be obstructed, and that usually, I would be writing more in the middle, or have things at the top, and that it might obstruct less things. That was my thinking. Also to not have to think, oh, I have this here, because I don't see it on my screen, right? Yeah. Okay, so I think I finally got it. I think it's finally makes sense. Alpha j here k is inferior to I, so k is 2. Inferior to I, 7, yes. And k inferior to j, or inferior or equal to j. So alpha, let's think about what alpha j is. I think alpha j, I think j, that's meant to be this 2, what I call 2 alpha, I think. So top right doesn't obstruct much. Yeah, I was thinking if I put my face somewhere, then it would be somewhere here, maybe, you know? I mean, yeah, I know viewer is not viewer is not particularly informative, but yeah, I was playing with it in Streamlabs, and so top right would obstruct less, you think? Yeah, thanks for the feedback. Definitely stuff that I'm still thinking of. But you're happy with the chat position, right? I mean, I quite like the fact that, like, you know, the chat is like slightly grayish background, and like the same thing with the bar. It seems like neat from my standpoint, but okay, cool. But maybe the whole music scrolling is actually distracting. It doesn't need to scroll. That's a possibility, right? Yeah. Thanks for telling me to tweak that. I definitely did that. And then let me remove the scrolling effect and see how that goes. Filters, and maybe that's less distracting. And I thought I had it all right. Then I think I need to change how I export things in Pretzel. Better, okay, yeah, because of course it was distracting. I didn't think of that. Okay, and then I align it this way. We can see if when it changes, if it's still properly aligned. Okay. So yes, right. I was trying to find what alpha j means, and I think it means 2, which is the local index. So I think that what we're saying here is that alpha and then superscript j is equal to, well, such as, well, alpha j, where j equal 2, I believe, here. Right, and j is lower or equal to, sorry, k is lower or equal to j. That's the whole point, that it's actually equal when we are on a single writer mode. When there's no replicas, then things are always properly aligned. But hold on, then if I say, yeah, if I, so ref of 7 beta is equal to 2 alpha, and that's a timestamp. And then alpha j, I should reference the paper paragraph if I could, but can't really, right? Unless I can put a hypothesis annotation on it. Is that possible? I think in theory it's possible. I'm going to try that. show highlights. Will it work if I just highlight this? It will, it will. Oh wow, that's so cool. Okay. Except it's hard to highlight on PDFs. That's the problem. So maybe I need to highlight the paragraph. Yeah, I think so. Or annotate. And post. I need to say something. So maybe I just need to highlight instead. Highlight. And then do I have the list of highlights? Yes. And then can I share my annotation? Yes. And then I can put it like here. Haha. Hey, thanks. Yeah, you know that's actually my other log entry right there. Filter Twitch chat spam. I can ban. Ban. Actually, if you want, I can give you reporting moderator rights. Mod. Does that work? Yeah. So you should be able to now click and ban if you want. Okay. Yeah, no problem. Hey, you have a sword as well. That's cool. Right. Did you see what I just did there, by the way? While we were getting spammed. So there's this awesome project called Hypothesis. It's at the website Hypothesis here. Nice. But you know, they're not very smart, right? Like they seem to be posting always the exact same spam. So it's probably possible to just filter that, although, you know, they will then change it and blah, blah. But yeah, so Hypothesis is this, this way to basically annotate the web. And it's sometimes used by, academics or journalists. And but the cool thing is that since we're on archive.org for the paper, then I think that this is now available globally. So actually, maybe you can try it. If I put this in the chat and you click there, tell me if, well, you're probably going to need to install a Chrome extension maybe, but maybe not. Maybe it will just actually open the PDF and show you my annotation. And if it does, then we're happy. Okay. So yeah, I think alpha j means index j in the local log, yes, and j equals 2, yes, and then k was equals to 2 as well, and so that's all good. That's all good. You can see the PDF, and can you see the highlight? Maybe for the highlight, you might need the extension. If you go down to page 5. Yeah, you might need to install the extension. Yeah, so I'll just put it in the chat if you want, but you clearly don't have to do this. But that's where you download the extension. Right. I'll also put this in the show notes. Or the log. Chrome extension is not going to be useful, and we had these things already. Okay. It insert the op after its parent. So insert the ops after its parent. So that's another thing we need to unpack. Yeah, that's right. That's the Chrome extension. So it inserts the op after its parent. I think that's when we're doing the rendering. So we receive the op, we know where the index is, and so therefore we know basically on screen or in the part of memory that's going to then be displayed on screen, or the state. We can do the insertion at position 2, meaning in this case we delete P. Unless in fact this preemptive CT sibling at that location, and so that's the merge case. Ah, right. Yeah, even to see annotations. Maybe that's not the best. It'd be better if you could read them without an account, and then if you need to, yeah, enjoy. Okay. I feel like I should implement just a tiny bit now, because, or at least modify my wrong implementation, because I've got a better handle on things, and it's maybe a good moment to start anchoring that a little bit into the programming. So Chronofold is this array, and that's okay. And op, we were saying, receive the ref, and it's a timestamp, and so timestamp is a thing, and I mean that's clearly way too big as a data structure, but maybe for now we say it's okay. And then I think I wanted to rewrite my test, right? So let's try and do that. Let's bring this thing up around here. So we have alpha 1. Oh, we have alpha, that's replica 1, beta, that's replica 2. We have alpha log. Is that the correct term? I think so, right? The replica, and then, all right, so it's not an array of ops. So we want the alpha chronofold first. So and that's what a chronofold is. So let's first write what our alpha chronofold is. And it's just an array of, well, clearly I don't want to build that manually, right? So append chronofold append string chronofold to an existing chronofold, right? So where we start with the empty chronofold. So that means that this is a, I mean, clearly we want to make this a monoid. But maybe I won't do that just quite yet. All right, because it's going to have insert as well as append, right? But okay, let's so append the string chronofold. It's going to be pretty much the same as this. Except you'll take a chronofold and a string and return a chronofold, and then append char or char chronofold will take a quote point. I think you need to take a quote point and an insert position, right? Well, append doesn't need to. Hey, well, did you see my YouTube? What I've played before starting to program on Twitch was Paraspera, which is a pretty cool game. Have you tried it? Yeah, so the append case takes the chronofold, and the chronofold is well, it's going to be entry, or let's say x's, right? Can we do this? No, we can't do this with arrays in Purescript. I forgot that. Are you? What does that mean? You mean what kind of games do you like? CP. So we're talking about appending at the end. So maybe we don't need to care so much about destructuring the array. Maybe. Yeah, is that easier to answer? Oh, interesting. I saw a YouTube video. This guy does reviews on games, and he was talking about this game that apparently like takes, I don't know, like 4,000 hours or something to complete, like a game that's really about waiting. And that was so interesting to me. Didn't play it though, but concept seems so interesting. Okay, Chronofold, and so I think I'm just trying to reinvent an array operation here. No, I'm not, because there is this, it is a linked list. Could it be that actually using a list representation, or in fact maybe a sequence or something? I mean, Chronofold, I mean, maybe using a list is an idea. I don't know. Right. Yeah, it's crazy, right? Yeah. Hey, you said you like waiting. I guess maybe not that much. Okay, I need to delete this. I don't need that. Transforming that into a quote point makes sense. Ah, yes. Right. Yeah. I did try EVE Online like a couple of years ago. It didn't stick, but I enjoyed the minimalism, the fact that there's a lot left to the imagination in some sense. But oh, you don't like games about waiting? Now I get it. Yes. So we just sounds good. So yeah, I mean, we need to deal with the linked list. And the fact that then it might imply mutation of, so is there a specific implementation for that's recommended here? Hmm. I mean, we want low cost inserts. So it seems like here, if we use some of the Haskell data type, like a sequence, for instance, I'm thinking of, that might be all good. That might give us what we want. But maybe I'm wrong. It's splicing free. But so the thing that I don't understand about how it stays splicing free is how it's the fact that it needs to update that M. It seems like if you insert something in the middle, then so there's something else that I don't understand, I think. Okay, nice. Yeah, so the thing is that so now I'm focusing on, you know, I guess the current state of affairs, right, is that there's basically sort of 4 data structure that we need to make all this go. And the sort of central one is the Chronofold, and that this thing that's described here. And it's just a, and each element in the Chronofold contains a code point, which is our character, and then a link to the next thing in a list. So as such, it's like a linked list, right? A linked list is something that where each element has a pointer to its next element. And if you store it that way, usually that's quite inefficient. Because when you insert something in the middle, then you need to kind of recalculate your links. Meaning, how can I draw a linked list? Usually, so the data type for list would be something like either you're at the end of the list, or you have an element, so a list of type A. You have an element and attached to a list. Yeah, it's that point that I'm a little bit fuzzy about the case where you're where because you're adding something in the middle of the list, then it seems like you need to recalculate the links coming in and out, right? So meaning, let's say we have a list that contains ABC, right? So a list that contains ABC is actually really going to be equivalent to a cons A with a cons B and then a const c, and then a nil. So this guy is the c, it's at the end of the list, and so therefore it's linked to nil. And then this guy b is actually linked to c, but it's actually linked to the tail of the list, to all the rest. So it's really linked to this const c, c nil, and then you put an a on top, and then there you go, you wrap it in an a. So basically const a points to the tail of the list, and then const b points to the tail, and then const c points to the tail, and then at the tail it's nil. Yeah, that thing, as far as I know, is how you is really the definition of a linked list, right there. So in languages like Purescript and Haskell, that's pretty much usually exactly the definition. So if we look at the tattoo from list, except maybe they do smart things here, and what maybe this data list is in the prelude, and no, data list is not in the prelude. What type of string lists? Okay, I'm confusing myself right now. Data list. Yeah, where are these? Right. No, I think of first in, last out. I mean, hold on. Yeah, first in, last out. Yeah, that would qualify. Although I think you would use that for queue usually, but I think you're right. Yeah. Yeah. Okay, I don't see the definition of the list here. Am I blind? And const head list. Yeah, that's all good. Where does list come from? It must be in the import. Okay, data list dot types. Okay, got it. List types. Here, yeah. So that's what I wrote here. That's usually the definition of a linked list in this functional programming world. And there's a way to make this more efficient by implementing it, for instance, as a sequence. And so I think that in Purescript we have this in ordered containers. Isn't that right? Ordered collections, maybe. Yeah, ordered collections. I think in here we have more efficient data structure. No, that's just for map and set. So is there a sequence for Purescript? Foldable, I mean capital S sequence. Yes, efficient general purpose sequence type. Why not just change what B points to and just add B plus point by copying what B pointed to previously? Yeah, that's right. I think the reason why I'm a little bit confused is because, well, it's the first time that I actually do this type of low-level data structure thinking. I mean, I've seen other people do it, and I've read about it, but it's my first time. So, but the other thing that's going on is that the paper talks of it as, I think what we want is actually what's called an immutable data structure, meaning, and I think that that's what we have here, because we're supposed to be splicing free, and I think that that's exactly what this means, meaning we can append thing to that struct, I think, and that we don't need to. No, I think that's right. Splicing free just means that we don't need to. Okay, splicing free means this, as I understand it, that if I have ABC, let's say neatly, neatly boxed inside some place in memory, right? And then I want to, let's say, add D right here. Then, if this is a contiguous array in memory, then I need to do something like, okay, first I take B and C, and I copy. Well, I might actually need to read C and right. I might need to take C and copy it at the end of the array, and then take B and copy it one step further in the array, and then finally I can insert my D, right? And so that's splicing, and it's obviously very inefficient. And so you don't want to have a data structure that makes you do that. Instead, you want, and so that's a contiguous array in memory. That's not a linked list. So instead, you want to store some kind of representation where you can, get ADBC, but without having to pay the cost of moving and shuffling all that memory around. So that's what splicing free means. And I think I was expecting that splicing free was also meant that we were having a data structure that's immutable. So immutable would be that we have this linked list. So we have const ABC nil. And so this representation is really not great to do that, but in this case, we would need to, if with this linked list representation, we kind of need to, unpack it, take the A out, basically. So now we have a const A somewhere, and then we have our const BC nil elsewhere in another part of the memory. And then well, we're lucky here, that's actually a pretty easy case. That's not very expensive for a linked list. We just say, okay, now it happens that you give me in addition a D. Well, that's all cool. Actually, it's not a const A. We can say we get the A, and then we have, so that's the head, and that's the tail. And then you give me whatever, we need to insert here. And so now that I have this, I can actually say, well, const A, well, yeah, the first step is actually to const D onto the tail. That's what we do. So we const D onto const B, const C, and nil. And then after we've done that, we still have our head A somewhere, right? And then we just const that. And now we have our new linked list. So that's expensive if you need to append inside the list, right? Because then you need to you need to keep things in memory and then reconstruct them. So we don't want that either. But I think this is this is a weave linked list. So maybe I should actually read on specifically what is a weave linked list. Maybe that will just help me understand this whole thing. I think this is described a little bit higher up, but basically what we want is something that's more efficient than any of those two things. And I'm trying to understand what is the trick that makes this go so that it's actually efficient. And so maybe just looking what the weave data structure is like will just help me out. Weave is a classic data structure for text versioning. It says that a weave has a reputation of one of the most reinvented data structures in history. It's quite cool. It alternatively knows that to leave deltas, union string, and other names. Its key idea is simple. Annotate all pieces of a text, deltas, with their birth and death dates. Keep the deleted pieces in their place. Okay, I don't see how that can be splice free, but now I get the idea of about deleted pieces. I think that that's what's specified here. That the weave, even though our text is pink, the Pinsk, the weave keeps the M, the delete, and the P. So, and that's why this is weave here. So that I get, but that's, to me, doesn't sound splicing free, right? That you need to splice in there. So weave is not splice free, I don't think. And so where do we get into how to make it not splice free? Maybe if we search for splice. Top issue, there we go. Top issue with the weave is that it needs to be spliced on every edit. Exactly. Rewritten in full, very much like a plain string. So we don't want that. So splice. Oh, what the? Okay. Where am I? Here. Splice. Find the next occurrence of the. Okay, no, I was. So there are two matches, and that's it. I think this text search is broken because there's at least splice in, splice free that we were seeing this thing here. Splicing free. Okay, so maybe I need to search for the prefix. Spliced, splicing. Right. Every data structure for version text has advantages and shortcomings. A plain text is the most simple, most extensively used data structure in the world. Unfortunately, a string is edited by splicing. Yes. Weave is the most natural data structure for diffing and merging, but editing a weave also requires splicing. Yes. A log is an append-only data structure, hence has O1 edits. So that's, I think, what we want. But recovering text from a log of edit is not trivial. Notably, log is a persistent data structure in the sense that every prefix of a log is also its complete version. So I didn't quite understand that. But the persistent data structure is a persistent data structure is something that basically keeps the history of its edits in some sense, where it basically, because you already have somewhere in memory const b, const c nil, then when you add const a on top, then you can just reference to the thing that existed before. And so I guess that's what is meant by the prefix of a log is its complete version, meaning that it has its history embedded in it. But right now I'm equating a log and a linked list, which is probably a big mistake. Similarly, any postfix of a log is a list of recent changes, okay, which is very convenient for replication synchronization. Piece tables are used by many text editor, have either O1 or logn edits, and may provide very limited versioning functionality. So ideally, we want a replicated version text data structure that is stored in an array, addressed by indices, needs no splicing, allows access to past version of the text, and merge of remote changes. We achieve this by combining a weave and a log. A chronofold is a subjectively ordered log of tuples, where WAI is the operation following alpha I in the weave. So the second element of the tuple forms a linked list that contains the weave, and thus any version of the text. And so this next, is it really previous? But or is it that ref is because we already saw that this was ref. And so ref is kind of previous in some sense. And so if we store next, the next is P. Sorry, I completely missed your question. Why not just change what B points to and just add B plus point by copying what B pointed to previously? I think we're asking a similar question. My concern is something like, so what I understand the data structure to be currently is this thing. So that's what I take from this struct here, meaning what I understand the structure to be is an array of these things, but maybe I'm wrong. And so it means that, for instance, we would have code point P, and then next would be or maybe I'm thinking about it reverse. So next is next really previous. I think that's the confusion there. Time for a break. I had yes, but at least I'll drink a little bit. The operation following alpha I in the weave. Right, we start with M. And the operation following alpha I in the weave. So let's say at index 0 or index 1, we start with M, and the operation following M in the weave, I would think is, at this point, is 2. Which doesn't make sense because there's no 2. And so really what we want to say that is like it's that terminator, is that it's that X is the end, which I call the top. And then when we type I, then M is then now followed by 2. And in the next cell, cell number 2 of our array, we have I, and then the end. That's kind of how I understand this data structure right now. But I think I'm wrong. 3 and 3 has n, and that n thing, and so on. And so, okay, maybe I should. So let's say we just have min and we want to delete p and so on. So then we would do what? We would add, well, it will be in 4th position in the array, or would it? So would it be in 4th position and then be called p? Or be called delete, a backspace, and point to 2. But that's not enough. What my problem is that it seems like we need to go back and mutate this to before. Because now M, and then that just seems like that's memory that's efficient at all. It's not a log anymore, I don't think. That's my confusion here. It seems like that needs a mutation here. By reading a chronofold like a log, we see the history of changes. So I guess that sort of makes sense. That we see the history, that we see that it was MIN before, and then we added this delete. And so let's do the next step. Then we add, then actually we, like the next becomes 5, and we, at position 5, we add, I think I will, this is position 1, and we have M4. This is position 2, and we have I3. This is position 3, and we have NT, and well, yeah, top. And this is position 4, and we have backspace 2. And then in position 1 we still have M4. And I need to use this. So write M2, I3, and T. And so now if we add P, then this now needs actually to point to 5, because what comes after backspace is P, and then what comes after P is 3. Two. So my whole problem is the mutation, which is not here, it's here. That's where the mutation occurs. And that doesn't sit right with me. But maybe it's fine. Maybe it's fine. Because this is actually, it could be actually fairly fast. It's just that we need to do bookkeeping, but maybe it's fine. But I'm not sure whether that's, let's look at the Rust implementation and see if we can gather how they did it. an entry into the Chronofold log. Okay, change. Oh, they differentiate an addition from a tombstone or a delete. Okay. Chronofold can be regarded either as a log of changes or a sequence of elements. The log index is zero base index log of changes. Each element is a visible, not yet deleted value of type T. You can edit the Chronofold in two ways, either by applying ops or by creating a session which has a vec-like API. Okay, so that's an implementation difference. And like vec, the Chronofold type allows to access value by index, because I think underneath, yeah, underneath it's a vec. The log is a vec of changes, and then there's some root. And then some the other structures are actually stored here. But next indices are separate here. They're not in the change T data type. You change T either insert, and T is it's polymorphic in T, but so it would be implemented for a code point, I believe, and then I think that's just some pointer related things. Perhaps the change, yeah, it's pointer stuff. Next log index. And we receive a change. Well, so that's not exactly what I want. Applying a knob to Chronofold makes sense, but so let's look at what the next indices is like. That seems like that departs from the paper. Set the predecessor's next index to our new changes index while keeping its previous next index for ourselves. Append to the Chronofold log. Self-log push change. Right, so as it adds the change to the log, it also sets next indices from new index to next index, or with a new index and next index. So there's something here that is part of the weave, the management of the links in the weave. But I think the implementation is not in the spirit of the paper, because here we have an array that includes the weave linked list. So I am a bit confused. But maybe it is just this. Maybe we just mutate and that's it. What does this say about weaves? For convention, a CT begins as 0 root atom, and the ancestry of each subsequent atom can be ultimately be traced back to it. Depth first pre-order traversal of operational tree is called a weave, equivalent to the operational array discussed earlier. Instead of representing the tree as an inefficient tangle of pointers, we store it in memory as this weave array. Additionally, since we know the creation order of each atom on every site by way of its timestamp, so I think this is different here from Chronofold, we can always derive a particular site's exact sequence of operations from the beginning of time. This sequence of site-specific atoms in creation order is called a yarn. A yarn are more of a cache than a primary data structure in CT, but I keep them around together with the weave to enable O1 atom lookups. To pull up an atom based on its identifier, all you need to do is grab its site yarn array and read out the atom at the identifier's index. Storing the tree as an array means we have to be careful when modifying it, or our invariant will be invalidated and the whole thing will fall apart. But I'm not worried about the tree data structure, I'm worried about the linked list data structure. But maybe I'm confusing myself again because it's actually sort of the same thing. Because when we're transmitting the ref here, with the op, that's the insertion point. That's enough to say where we're going to, how we're going to relink the list. I think this is confusing me more than anything. Okay, let's see. The second element of the tuple forms a linked list that contains the weave, and thus any version of the text. Has to find the op's position in the weave and relink the linked list to include a new op at that position. So that sounded, that's that mutation, the relinking. And I don't see how we can do that with that mutation. Okay, maybe this will actually explain it. Chronofold and co-structures. Stanislavski written by author 1, corrected to Lobachevsky by author 2. Next 13. Yeah, so I guess maybe that's why in Rust the other developer put it into another structure so that you don't need to mutate the log. You just have another array or vec for that. Yeah, I think maybe that's, they call this an offset map. Is that a, oh wow, that's an actual library data structure. Log index would be the local index, and so, and relative next index would be that. So you'd say you modify 2 to 4 by doing this. Self next index get, and then you set it to the current index with the new index. And so that's done here with a different data structure. But and here, oh, it could be that that's just in the further optimization that they were talking about. We further optimized that in section 4, and I've been not looking at section 4. Because that next thing, doesn't seem like it's inside the array right here. So maybe that's the whole point, that we also store the next somewhere else. The text within a Chronofold becomes a sequence. The next NDX author and shift co-structure. Yes, indeed. Next NDX become its own co-structure. In a typical Chronofold, most of the next NDX pointers would be equal to 1i+1. Instead of spending memory for every such value, we may offload them to a separate sparse array. There we go. So it's not just the offloading to a separate sparse array, it's just the offloading as well. It's not just the sparseness, there's also offloading. In the resulting implementation, a thin Chronofold is simply a log of UTF-32 code points. As yet another optimization, we may notice that's it. I think I understand it now. So let's write this down, and then I will have dinner and probably end the stream here. But I think I understand now. So indeed, this 4, yes, it needs mutation here. Yes, yes, it does. So now our Chronofold actually doesn't really have next in it. So that's Chronofold, but in practice we use a thinned Chronofold and offload the linked list management to a separate co-structure, which means that this is just an array of cut points. So an array of values, and then we have it's called next NDX. Okay, next NDX, which is really the weave structure, which is something which is probably this offset map there in Rust, which is something that takes a local index. I mean, right now we can approximate it into an array of of an index, which we say is an int, and an int to a next, which is also locally an int. It's really an index into the so okay, let's say that we did I use ints for something else? I mean, yeah, I think we just say type index equal int, and we can remove those. And so that's the next NDX data structure, which is meant to be a sparse array. Or let's say it could be a sparse array, and then note that it's an offset map in Rust. In the Rust implementation. And we optimize all this later, but yeah, and so clearly we mutate that thing. Okay. But then we don't need, but then we can keep our thin chronofold as an append-only structure, which it couldn't be if it was in this representation, because we need to go in it and mutate it. That's cool. Okay, I think I'm ready to sign off and then start really implementing more of that stuff tomorrow. So thanks a lot for following. Thanks a lot for your feedback, and see you tomorrow around the same time.